So looking at problem 1 on that handout, you have some tornado, and at its peak, it's 60 meters in diameter, 500 kilometer per hour winds. What's the angular velocity in revolutions per second? So I am going to start with the linear speed that's been given, and I'm going to use that conversion, that thing we haven't seen for a while, that railroad track thing, and I know that I'm dealing with a speed of 500 kilometers per hour. And I want to know what angular velocity is in revolutions per second. So I'm going from something linear to something rotational. So I'm going to have to do some things here. But first off the bat, I just need to get this into uh, uh, compatible units. I either need to get my meters into kilometers or my kilometers per hour into meters per second or something. So I'm going to go the speed into what it needs to be. So I know that every kilometer has 1,000 meters in it. That's a fancy form of 1. And I know that every hour has 3,600 seconds, 60 minutes times 60 seconds each. And so the hours drop out, the kilometers drop out, and I'm left with 138.9 meters per second. That's the meters per second speed of this tornado. And again, I want to go from linear to angular, so I need to use the equation that relates those two things, V equals omega r, all right? And that means that my angular speed, which is what if I'm going to get to revs per second, which is an angular speed, it's just not in radians, it's in revolutions, the thing that we're most familiar with. This is just going to be V over r. So I take 138.9 meters per second and divide by the 60 meters given in the problem. Again, I could have just gone straight to this, but I would have to do some conversions. All right, there would be no escaping the conversions. And if you do this, well, here's the thing is the meters are going to drop out of this situation, and you're going to be left with something per second. And that something per second that you're left with is 4.63 radians per second. That's we talk about angles in that regard. Yes. Yes, we need to change our 60 to 30. I wasn't paying attention. The answer's correct. I just wrote in 60 instead of 30. I even have 30 on my notes, but I wrote 60 on my slide here. So it's still, the answer's still 4.63 radians. I just, thanks for that, catching that. You guys are required to catch all the mistakes, which I planned that one, by the way, just see if anyone's paying attention. Yeah, yeah, right. So we have this omega. Yay. So omega, so I'm going to do the same thing I started with. Now that I have an omega that's in radians per second, I need to convert it to revolutions per second. So I'm going to do that. I'm going to have 4.63 radians per second. I'm going to use this conversion chart thing. And I know that there are every revolution, complete trip around the circular path would have 2 pi radians. Well, that means the radians fall out, and now I have revs per second. And if I finish the math, I get 0.737 radians per second. This is just sort of I'm sorry, not radians per second. All that trouble, and I went straight back to radians. Revs per second. A lot of times you are given revolutions per minute, like your engine has RPMs. A lot of gauges that do that are revolutions per minute. We wanted revolutions per second. So this tornado, and it makes sense, you've seen them. You know, it's big and it's clunky and it's moving, the whole thing. you know, it's how is it sweeping out this angle? All right, but it's also pretty darn big. 30 meters is 30 yards. Okay, that's a pretty big tornado. I want to go somewhere else. So there's that. That's all there is to that problem. Simple. Basically, it's conversion. Put speeds in a certain kind of unit, convert that speed to an angular speed, convert that angular speed to another kind of unit. So it's sort of nuts and bolts kind of work. These first few problems are of that type, where we're just um, going over some of the basic mechanics. So number two, an ultra centrifuge goes from 0 to 100,000 RPM in 2 minutes. I think bacterial flagellum motors can do a quarter. They can turn a quarter turn. Uh, they can go faster. They don't have to wait so long to speed up. They can go from 0 to insane speed in the quarter turn. Anyways, as a side note, what is the angular acceleration in rads per second squared? What's a tangential acceleration? So this is another let's convert and compute kind of problem. So these are basics setting up for doing more complicated problems. So let's look at part A here. We're given that there is a angular speed of 100,000 RPM. So I write from the first sentence, 100,000, I can write that as 10 to the fifth revs, and I have so many of those per minute. And here's the thing. Why am I changing revs per minute to something other than that? Well, I need it to be in radians per second because that's the proper unit for all of my angular kinematic equations and my angular dynamics equations. Kinematics is just motion without respect to the cause. Dynamics is motion with respect to the cause, namely forces. When I'm dealing with angular quantities, it's always radians. Never revs, never degrees per second. It's always radians per second squared, et cetera, et cetera, et cetera. Yes?
Just a question of clarification. So it becomes 100,000 RPMs in 2 minutes. Does that mean its acceleration is 50,000 RPM
No,
per minute? So
that's not it.
10 to 50.
So we're just converting the angular speed right now. We're not to the acceleration part. Okay. So 2 pi radians per rev. And again, uh, a minute is going to be 60 seconds. So the revs drop out, the minutes drop out. Now I have some number of radians per second, namely 1.047 times 10 to the fourth radians per second. So step one in any of these problems, if you're not given radians per something or other, you got to convert to radians. Get everything in radians first so that you can um, do that. But it asks, what's its angular acceleration in radians per second squared? Well, now I have that. It is the case that angular acceleration is delta omega over delta t, or in this case, it's just going to be omega over delta t because I started from rest. The initial part's not there. All right. So now I take the 1.047 times 10 to the fourth radians per second, and I divide it by the 2 minutes, which is 120 seconds, and I'm going to get 87.3 radians per second squared, because this is an acceleration. It's always, or radians per second. All right, it's that speed per second relative to how many seconds. So now I've answered part A. Yay. Part B. Was asking what is the tangential acceleration at a point or of a point that's 9.5 centimeters from the axis of rotation. You may not recall from our prior unit where we dealt with circular motion, but the tangential acceleration is related to the angular acceleration by means of the radius. Namely, tangential acceleration, a sub t, is angular acceleration alpha times the radius r. We just found alpha r, and we already know the radius. So this one is relatively simple. 87.3 rads per second squared times the radius, which in meters, it needs to be in meters, is going to be 0.095 meters. And so we get 8.29 meters per second squared. So easy peasy, but we just had to do a conversion so we could get that angular acceleration or tangential acceleration first. And then part C, what is a radial acceleration in acceleration, meter per second, and then multiples of g at full RPM. So we're going to need to find the centripetal acceleration. That radial acceleration is centripetal acceleration, meaning inward along the radius. That's what we mean by radial, inward along the radius. So this is asking for centripetal acceleration, prior unit. That was v squared over r. We just used this last week in our gravitation stuff to figure out a orbital speed using Newton's second law. So v squared over r, well, I don't know linear speed v, but I do know that v is omega r, which means that I'm going to get omega squared r. We also created this equation a while back in that other unit, but I just sort of redid it here because we can. So omega squared, let's see, omega was our 1.047 times 10 to the fourth number. I'll just leave the units off. That's getting squared. The radius is still at that 0.095 meters. And so my centripetal acceleration ends up being 1.04 times 10 to the seventh meters per second squared. That's a lot. That would be, well, that's 10 to the seventh is 10 million, all right? So essentially 10 million newtons per kilogram to make that conversion. But then it wanted that, and it wanted this in terms of the number of G's. Okay. If I take the centripetal acceleration relative to G, okay, which that'll be with a 9.8 if I just divide that, then I'm going to get roughly a million G's out of that. This is an ultracentrifuge. I think you guys use a centrifuge. I don't know if it's an ultra one or not in the chemistry, biology areas. I know they have them. I don't know if they use them in class or they just use them in the prep area. Do they use them in class? Great. So you've used a centrifuge, whether it was an ultra one or not, I don't know. But they get cranking. And, it takes a lot of force to separate the component parts of various fluids away from one another. And so the fluids can handle the G's. We can't handle more than about 20. So a test pilot is likely to pass out at 20 G's. This is a person who's used to it and whose genetics have favored them to tolerate such things. But we could also kill the pilot at 20 G's. All right. So in fact, just a interesting side note, the F-20, or F-22, which was later replaced by the F-35, I think, but it was so advanced that they had to, the control systems on that plane, they had to engineer the control system so that the pilot couldn't let the plane do what it could do. Because the plane could turn so fast that it would put more than 20 Gs on the pilot. So they actually had to put all sorts of various limits. So if we ever get around to remotely flying jets, like you've seen in some movies, they will do some crazy maneuvering things because if there's no living being inside of the plane, then it's a matter of structural integrity of the plane. That's the limiter. And steel can do more than bone and flesh as far as handling those sorts of stresses. Meanwhile, back at the ranch, we were doing physics problems. So number 3 was now that we're going to start to pull in some of the other physics uh, from the course. And that's why this last unit kind of serves as a final exam because you have to use everything that came before it, sort of like algebra courses. Every test's a cumulative test because you need all the stuff that came before. So we have a grindstone. It's 90 kilograms gross mass, and it's got a radius of third of a meter roughly, and it's going 90 RPMs. You press a steel axe against it with a radial force of 20 newtons. That's a frictional force. I mean, because what's that axe going to do? It's going to slow it down, right? Because it's resisting. There's a surface interaction. There's friction coming out of that puppy, and things are going to get hot. So part A, assuming the kinetic coefficient of friction is 0.2, calculate the angular acceleration of the grindstone. So, right off the bat, I know that friction, and it's kinetic friction, so I'll use a sub K on this. Friction is always defined as the coefficient of friction times the normal force. So we use N for our lowercase n as a classical symbol for a normal force, the surface reaction force. This is entirely linear, even though it's happening even though the two surfaces are facing one another vertically as far as you're concerned, okay, um, that still is a perpendicular surface to surface reaction. So I have no components, no trig, no minus or plus, whatever. So this is just going to be straight up this way. So now I can say, well, I was told that 0.2 was the coefficient of friction, and they told me that I'm applying a straight on 20 Newton force. That means this reaction force is going to be the same magnitude, so 20 newtons. And so I'm going to get 4 newtons of friction force out of this puppy. All right. So torque, I'm going to end up torquing this situation. And so torque, in general, we did a lot of complicated torque metaphors and analogies showing how all these equations equal it, but it's essentially a radius times a force, is it not? That is functionally what we wrote out, and fundamentally that is what it is. Excuse me. And so it's an opposing force, so it's going to be negative, and it's going to be friction in this case because friction is the force that's being applied here. All right, and it's going to be done at some radius, namely the radius of the grindstone, the spinning thing. The force is being applied at that distance. So all torques are a force distance idea. More simply, if you've ever changed a tire on a car, hopefully you had a cheater bar because those stupid little twigs they give you from the car, you pick your teeth with it better than you could change a tire with because they're so small. The first thing you do is go out and buy one of those 4x4 lug things. Why? Because the longer the lever arm, the bigger the multiplier of the force is. If you have a cheater bar that's a meter long, you won't have to hardly do any grunting to move or strip the lug, no, bolt, all right. But if it's shorter, it's going to be, you got to push harder. Okay, it's sort of like pushing the door open from the middle versus the edge. Same idea here. It's harder to see with this one because nobody puts an axe to a grindstone anymore. All right, so this problem sort of, it's historical. You're a better person for understanding the history. Well, we also know this question's aiming at what's the angular acceleration. and all I know is friction. But I know that I have friction, a force applied to a roundy thing at some distance. Ooh, that means torque. So I can use the two things that I know, the radius of the thing going roundy and the force that's doing this torquing business, and I know that torque is also equal to I alpha. If only the people watching this video in the future knew about the lights going on and off because nobody's moving. Because everybody's just riveted. They can't even imagine how exciting this is. Now, the thing that you don't know yet, however, I did allude to it, and when we look in our book later, you'll find a table, or if you just Google rotational inertia, you'll see an image of a bunch of different shapes, rods and balls and hoops and wheels, and there'll be all these I equals something that has an mr squared in it. All right. And so this situation, a disk, the rotational inertia of a disk is 1/2 mr squared. Okay. So for our purposes, the rotational inertia of our grindstone is 1/2 mr squared. It's what it works out to for a disk. It's mr squared if it's just a ball, and it's 1/12 mr squared I think if it's a uh, mass concentrated at the end of a rod. I mean, there's all these different formulas that we won't derive. We'll just trust that the people who thought of them didn't lie. Okay, so we have this going for us. And so what we can do is, now that we've put all these things together, that's why it pays to have all those metaphors and analogies. Is, oh, I'm a little bit of this, a little bit of that. I can put them together and get what I'm looking for, because you've seen multiple faces of torque, if you will. All right, it's an I alpha, it's an RF, it's an XFY minus YFX. It's a lot of different things, and depending on the nature of the problem you're trying to solve, which thing I grab. If I need to hammer a nail, I get a hammer. If I need to screw something in, I get a screwdriver, not a hammer. I mean, it works, right? I mean, pound a screw into the wall with a hammer, it just doesn't work out as nicely. Anyways, so all of this to say that I can pull alpha away and write it as negative 2f over the mass times the radius. All right, and so that is basically taking this and this. Let me go to that. All right, I know about the friction force and the radius. I know that that extends out via Newton's second law version, I alpha, into other things that I know, namely the mass of the grindstone. I already knew the radius, but now I have something that lets me get to that alpha. What's the angular acceleration that this thing is going to undergo? And so if we start plugging and chugging stuff into here, we'll get -2 times that 4 newtons of frictional force. The mass of 90 kilograms is given in the problem, and the radius of the wheel 0.34 meters. And that means my alpha ends up being a negative 0.26 radians per second squared. Why is it radians, you say? Well, know that a Newton, okay, a Newton is defined to be a kilogram meter per second squared. So what's going to happen is this kilogram and that kilogram drop out unit-wise. This meter and that meter drop out unit-wise, and you just have something, you have some number per second squared. Anytime you get a pure number per second squared, that's radians, especially since we're dealing with roundy stuff. Okay, so we done it. That's part A. Part B. We want to know how many turns will the stone make before going, this grinding stone before going to rest. Well, we know it starts off at 90 revolutions per minute. And I'm going to keep doing this speed conversion bit as your starting point. If you have speeds that are not radians per second, you need to immediately convert them before you try to do anything. All right. So you could just do that initially and then have it all before you start crunching, or you can do it as you go. So revs per minute. So there's 2 pi radians per rev, and a minute has 60 seconds. So the revs drop, the minutes drop, and we get 9.425 rads per second. You can also, we have this, remember, omega squared minus, so the difference in speed squareds, regardless of what kind, are double the acceleration and displacement. So I just wrote it in angular variables. So what this gets me to is my theta, because it wants to know how many turns will it go. So I have to, if I'm going to say turns, if I'm going to say turns in revs, I have to get it into radians so that I can let the kinematics run its course, which demands radians for rotational variables, and then I convert those radians, the number of angle things, then I convert that to revs. All right. Otherwise, you'll get your wires crossed and have a bad time. So we're going to have 0 minus this 9.425 squared over double the acceleration. I dropped the units because they're already the correct units, so I don't have to really bother with that. And this gives me 170.2 radians. Again, I need revs because it wants to know how many turns will it, in one sense, 170 radians is acceptable. And that's going to be a lot of turns because 6.28 radians is one trip around. All right, 2 pi is only 6.3 radians roughly. So again, same old business. A rev is 2 pi radians. So radians drop, and this means that you would have roughly 27 revolutions. So that one kind of pulls some of the new stuff in with some of the old stuff. Now number 4. With the aid of a string, a gyroscope is accelerated from rest to 32 rads per second in 0.4 seconds. So everything comes out of the box in the right units. We don't have to bother with this. What's angular acceleration? All right. Well, omega equals omega naught plus alpha t. This is just the second zeroth law for angular things. Speed, final speeds, initial speed plus acceleration times time, or the change in speed. These are in angular terms. So this means that my alpha would just be omega over t, since this is from rest. And so if you crunch those numbers, 32 over 0.4, you get 80. rads per second squared. Part B wants to know how many revolutions does it go through before it, and during this process of being accelerated. So again, I'm just going to, since it started from rest, I don't have a change in delta theta. So and I don't have an initial um, speed, it's 0. So I can just write 1/2 alpha t squared, sort of like our height equation for dropping from rest, except this is a little different. So we get 1/2 of 80, that was the acceleration, and the time squared, 0.4, and that gives you 6.4 rads. And then, of course, if you convert that to revs by this 2 pi business, then you get your theta. Basically, it's 1 rev, because you basically have 6.4 over 6.28. It's a little bit more than 1 rev, but it'll round to essentially 1 revolution. So that's number 4. Pretty basic one. We got room to squish 5 in here. Maybe even number 6 for all I know. So suppose a piece of dust finds itself on a CD. Nobody uses CDs anymore. If the spin rate of the CD is 500 RPM, piece of dust is 4.3 centimeters, what's the total distance traveled, or meaning what's its angular displacement? And then ultimately I can convert that to a path length, actually an arc length. All right, so theta, once again, would be the initial, final position is initial position plus the change, which would be speed times time. So it's using the kinematics. So 0, and I got to convert this 500 revs per minute. I can't use revs per minute. I can only use radians per second. And minute 60 seconds. So that's my omega right here. That's omega, had to convert it. And then the time was, oh, it's in minutes already. Let's do this. I'm going to erase this last part here. Hopefully you're not writing in pen. Because then I can just let the minutes drop out. So minutes drop out here, revs drop out. That way when I compute this, theta ends up being 3,000 pi. That's a lot of pi. So what about an arc length? Well, it is the case that arc length, going back to not only earlier in the course where we derived this from basically geometry of the circle, but you would have seen this in a trig or pre-calc class. So it's r theta. The radius was given as 0.043 meters, and we just found 3,000 pi as the angular displacement, or final position from 0, if you will. And so the arc length, okay, because some number of pi times a number of meters, just number of meters, 405 meters. So a piece of dust on a CD, moving it at 500 RPM, will travel more than 1 football field, almost 1.5 football fields, path length on a roundy course. Okay. No room for number 6. So we'll keep on moving here. Six, gyroscope, another gyroscope. Going at an initial rate of 32, just like before. Acceleration, it slows from that speed to rest by this acceleration or deceleration of 0.7 rads. How long does it take to come to rest? All right. So part A wants to know how long. So I have an equation, the second zeroth law for rotational motion, which says the final angular speed is the initial angular speed plus the acceleration times time, otherwise known as the change in angular speed. This means since it's going to a final speed of 0, okay, I'll write it this way. We have a final speed of 0 minus the 32 that it starts at over a negative acceleration because it's slowing it down. So the problem didn't give you negative 0.7, but it told you it's a slowing down rate. Therefore, you have to put the negative on it. And so the time that this takes is going to be 45.7 seconds. Part B. Here's the full-on displacement equation in angular terms. The last time we saw this, besides some problems you must have done in homework, was when we developed the average speed formula from graphical analysis. And so initially, this position would be 0. So what this is going to boil down to is that our theta will just be the speed and time, the speed that we start at and the time that it goes, that initial speed, plus half alpha t squared. So theta is going to be a 32 rads per second times 45.7 seconds, how long it takes to decelerate, plus 1/2 of our negative 0.7 rads per second squared times the 45.7 seconds squared. So in the end, you do all this crunching, you get 731 radians. That makes sense. We would expect a lot of roundy in 46 seconds almost at a speed of 32 radians per second. That's like, 5 times around in a second. Okay. Well, it's radians. I want to know revs, how many revolutions it makes. So I just go straight to conversion. 1 rev is 2 pi radians. And so the radians drop out, and you get 116 revs.